So our conclusion, it is this theorem, minimum square error theorem. Yeah. All right, so let me describe the whole thing together. Yeah. When we start, we are given a periodic function, f function. And we also know its Fourier series exists. We can calculate its Fourier series by our, the formulas. Yeah. Then we want to do approximation. So when we do approximation, we use trigonometric polynomials of degree capital N, the polynomial in this form, trig polynomial in this form, yeah, to approximate original function. But the error definition, we choose the square difference error, like this. The difference, square of difference integral, that error. All right. So with this error, then, based the calculation we did here, yeah, so we find the result. Yeah. The result is, when the capital A, capital B coefficients are chosen the same as the little a, little b coefficients, then we get the best approximation. That's the conclusion. Yeah. You can choose whatever you like, but at the end, the best approximation comes from the Fourier coefficients. How about that? So Fourier coefficients, we have the best approximation. Yeah. If people ask you, what do you mean best approximation? The error defined in this way is the smallest. The smallest error, that is, this E star gives us the smallest error formula. Yeah, so that's the conclusion. Okay, yeah. So we put this, the whole thing together in a theorem. Yeah. So we call this minimum square error theorem. Yeah. So, yeah. So yeah, we will see that. Okay. All right. Minimum square error theorem. All right. Let me just quickly go through this error. After that, we will look at the application of this theorem. All right. The square error of f in equation 2, what is equation 2? This is equation 2. The error, capital F is defined by this equation. Equation 2, with fixed capital N relative to f on interval, is the minimum if and only if the coefficient of capital F in equation 2 are the Fourier coefficients of little f, and this minimum value E star given by equation 6. This is equation 6. Yeah. That's the theorem. Okay. Yeah. Minimum square error theorem. Yeah. Then after that, with this theorem, we have the confidence given the function, periodic function, with the Fourier expansion, with, valid, reasonable Fourier expansion,
So let's say once we arrive at the coefficients we need to satisfy equation 6, I suppose that we evaluate that, right? The integral of the series. Do we evaluate those? Or is this just the representation of what the square is?
if you choose Fourier series, you evaluate this is the definition of the error, you will get this formula.
So are we supposed to get like a closed form solution when we evaluate it?
Oh, closed form for the error, okay? Right. Error part. Yeah, right. Closed form for the error part. Yeah, error. So you can represent. Yeah. All right. Yeah. All right. Yeah. Okay. This theorem has many applications. Yeah. All right. So next we look at the applications. Yeah. All right. The error part. Yeah. Because the error part, and you also know the E star. Can you see the E star must be greater or equal to 0? The error part. E star. Because E star comes from that E. That E, you have square integral. Is it always greater or equal to 0? Yeah. Any E is non-negative, right? Yeah. The definition of our error can never be negative, right? Yeah. So because this definition, non-negative. So this E star is non-negative, right? You can see that. Yeah. All right. Next slide. So we derive several properties from this theorem. Yeah. All right. Bessel's inequality and possible identity. These two results, yeah, derived from the theorem, okay, minimum square error theorem. Yeah. All right. Yeah. So that's the setting we have. Yeah. All right. Now, first thing, E star representation, like this. Yeah. E star, non-negative, right? Yeah. Based on, because E star is a special case of E. Special case of E. Okay? And E always greater or equal to 0. Yeah. Yeah. All right. Then we can say E star always greater or equal to 0, right? Yeah. When E star greater or equal to 0, can we write this inequality? This is the inequality, right? Yeah. Because that is directly, it comes from this E star, greater or equal to 0. Yeah. So we just move, yeah. So this inequality is true. Okay. When it is true, that means it is true for all capital N, right? Yeah. Because we can choose any capital N. For any capital N, this inequality is true. Yeah. All right. Can we push capital N to infinity? When we push capital N to infinity, it's also true, right? Yeah? We can push capital N to infinity. It's still true. All right? Now, so we get this Bessel's inequality. We push to infinity. Yeah. But when you push to infinity, it is also true. So we call it Bessel's inequality. Yeah. Yeah. Directly, this result comes from minimum square error theorem. Okay. Yeah. All right. All right. So next, yeah. Now we go another step further. Yeah. So this is our Fourier series expansion. Okay. All right. Now, this time, we change our view a little bit. So what's the view? Remember, the system, the basis functions I talked about last time. Yeah. Because when we form a trigonometric system, we use all these functions to form trigonometric system. All right? And we say these functions form a basis of the trigonometric system. So what's the meaning of basis? Basis means you can cover, use these basis functions, you can cover all the functions. So what kind of functions? All the functions Yeah. Remember last time I said square integrable functions. Yeah. Okay. Yeah. So all the functions with the property, the integral f0 dx less than infinity. The functions, yeah, the square of this function, its integral is limited. All these functions, we can use these basis functions to represent, to approximate, yeah, all right, using the Fourier series to approximate, yeah, all right, and the approximation we get, we call, so here, the completeness of the system. Because when we talk about the basis, the reason we can call it a basis, it must have this completeness property. What's the completeness property? Yeah. It cannot miss any function any function. It can represent all the functions with this property. It does not miss anyone. If you miss a single one, we cannot call it complete, right? Yeah. So your system is not complete because you miss one, right? So it cannot miss anyone. Okay, it covers all such functions, all these functions. Yeah. So by the completeness of the system, yeah. All right, completeness of the system, we can get Parsifal's identity because we cannot miss anything, right? Yeah, we do not miss anything. Okay, yeah. All right. The Parsifal's identity, there you change the Bessel's inequality here, this place, less than or equal, because less than or equal, you're not sure if the system is complete or not, right? Yeah. So even if the system is not complete, yeah, this less than or equal to still holds. Yeah. But you move to the next level, you know the system is complete. Yeah. The system covers, everything. Square integrable. Everything for the square integral functions. You do not miss anything. Okay? If you do not miss anything, then the difference between these two, left-hand side, right-hand side, is 0. If the difference is not 0, you miss something, okay? There is a gap. You miss something, all right? Yeah, there is a gap. Yeah. There, because the system is complete, we do not miss anything, okay? Nothing is missed. No gap between those two numbers. For that reason, we get this Parsifal's identity. We can prove it. We can prove it. Okay? The Parsifal identity, we can prove it. Yeah. Yeah. All right. Yeah. All right. Yeah. So these two inequalities, these two results. Yeah. But for the Bessel's inequality, yeah. Yeah. So it's a very general inequality. That means even the system is not complete. We can use this inequality. Okay? All right. Yeah, you can represent any function. Yeah, yeah. So, all right. Now this one, other functions, other system you want to use. Yeah, yeah. So you have the Bessel's inequality. Yeah, but when you want to move to the Parsifal's identity, you have to make sure the system is complete. Yeah. Then you can use the Parsifal's identity. Yeah. All right. Yeah. Next, B.2, minimum square error for the sawtooth wave. Yeah. The shape sawtooth. Yeah. Sawtooth. Yeah. Up and down. Yeah. Tooth. Saw, like a saw. Yeah. That function, periodic function. Yeah. So let's calculate the minimum square error, Parsifal's identity, and so on. Yeah. We want to, use Parsifal's identity and see what interesting result can we get. Yeah. All right. Yeah. Fourier series of sawtooth wave. This is the sawtooth wave. The shape like this. And the function, define the sawtooth function. Yeah. We only need to define one interval. Yeah. Then we expand, yeah, by the periodic function properties. Yeah. All right. On one interval, x plus pi, a simple function, x plus pi on this one interval. Okay. All right. Then for other intervals, yeah, we have this periodic property extension. Yeah. Periodic extension. Yeah. All right. Then now we want to calculate Fourier series, Fourier coefficients. Yeah. When you calculate Fourier coefficients, yeah, here we want to use some special properties. Special properties to do the calculation. Yeah. Yeah. Remember, even function, odd function, we used the last time, the even function, some symmetry, right? Here, this function, if you look at the definition directly, look at the shape, it's not an even function, and it's not an odd function. Okay? Yeah. Not an even function, not an odd function. Yeah. But, if you ignore this pi term, it's an odd function. So the difference with the odd function is just the pi shift. Your plus pi, if you use x function, x is an odd function, right? X is an odd function. Yeah. But you shift pi units up, you get this function. Yeah. So we represent the seesaw function, not seesaw, sawtooth function, f1 plus f2, and f1 is the odd function, and f2 is the constant function. Yeah. So we split it into as sum of two functions. Yeah. All right, yeah. Odd function, we know, it's a Fourier series simpler, right? We can calculate. Because 1/2 of the coefficients gone. We only calculate the other half, yeah, sine half. Cosine half gone, okay? We only calculate the sine half. Yeah. All right. Yeah. Sum and a scalar multiple, yeah, so that's property, yeah. The Fourier coefficients of a sum, f1 plus f2, are the sums of corresponding Fourier coefficients of f1 and f2. We can calculate them separately. Let's calculate f1 Fourier series. Let's calculate f2 Fourier series. Then we add them together, we get the Fourier series of f1 plus f2. The linearity property, yeah? We know integral has the linearity property. Yeah. The Fourier series, we use integrals. Integrals has the linearity property. Yeah. So that's why we have this theorem. Yeah. All right. Yeah. Let's apply the simple theorem to do the calculation. Yeah. All right. Yeah. Yeah. So here we say this is already the Fourier series. Yeah. We do not need to do calculation for f2. Because this constant, can we treat this constant? It is already the Fourier series of f2. Yeah. The first term. Yeah. This is Fourier it only has the first constant term. Yeah. All other terms, sine terms, cosine terms, all other terms, all 0. Yeah. So that's f2. We don't need to calculate anything. We only need to calculate Fourier series of f1. Yeah. All right. f1, odd function, yeah, we just calculate the b coefficients. Yeah. Let's use the formulas for the b coefficients to calculate f1. All right, yeah. Yeah, so let's plug in f1, yeah, f1, that's x, yeah, okay, yeah. So cosine, yeah, so then calculate, yeah. Then, after calculation, we have this. Yeah. Third integral, 1 to this one, yeah, all right, yeah. So here, yeah, so yeah, because, so here, I use this differential. So I put this sign into the, d, differential. Because derivative of cosine, you have negative, right? Yeah. Then the constant n, you need to divide it by n to cancel out. Yeah, differential, okay? So when I do integral by parts, then I make this form, integral by parts, okay? Remember, u dv, right? Yeah, we do this u dv. Yeah. So when do you negative sign, constant, we need to adjust. Yeah. Because most students, yeah. So usually I write directly. Most students, they need to, u, put a u, and put a v, yeah, write explicitly. Then use the integration by parts. Yeah. For me, I use the differential way because we have the differential concept, right? D. Yeah. Let's just work using the differential concept. Then I just write all the way down. Okay. Yeah. Yeah. When I did grading, many students, because they do not feel comfortable using the differential concept. Yeah. So they need to, on scratch paper, write u equals some function, v equals function. Then integral u dv equals, write that part out. Yeah. So, yeah. So a little different. Yeah. Differential. Yeah, we have differential. Why we just use it? Okay. Yeah, it's okay. Yeah. All right. Yeah. Okay. Yeah. Yeah, but you know how to calculate integral by parts. Yeah. Just get used to this way. Yeah. All right. Cosine n pi, n could be even odd, right? Yeah, n could be even odd. Okay. When n is even, cosine even number of pi 1. Yeah. When n is odd, cosine odd number pi -1. Okay. So positive 1, -1. Yeah. Alternatively. All right? Yeah. All right. So let's write this BU coefficients based on that. Okay. Yeah. Constant 2 factor out. Yeah. So then, the sign, yeah, we need to, switch. Yeah. Alternative sign. Yeah. Alternatively. Yeah. Then, but F2, because F2, so here, F2 is a constant. We just add F2 to the constant directly. Yeah. Because, so here, yeah, B0 is 0, right? The constant part is 0. Constant part is 0, but this pi comes from F2. So pi plus that B0, 0, yeah, so we get a constant pi. So this is the Fourier series for the f function. Fourier series of f function. Yeah. Very simple. Yeah. After we find the Fourier series of f function, can we apply the Parseval's identity? Remember Parseval's identity from the Fourier coefficients. Okay. Left-hand side, square sum of squares of all the Fourier coefficients. Okay, yeah. So with some constant. Yeah. All right. So here, yeah. So that's the E. Yeah. Although it's we calculate the error E. So here we want to calculate the error. Okay. Yeah, before we apply the Parseval's identity, let's calculate the error. Okay. Yeah. Definition E star. Yeah. So we use the Fourier coefficients error. All right. Yeah. Yeah. So if you look at the approximation, the graph like that. All right. When n goes to infinity, all right, E star goes to infinity. You know. Yeah. From the graph, you can see that. Yeah. The error becomes smaller, smaller. Yeah. Yeah. All right. Then, Parsifal's identity. Because in the Parsifal identity, you need to calculate from negative pi to pi f squared, right? Yeah. You need to calculate that. Yeah. Now let's calculate. Let's calculate. Yeah. The left-hand side, yeah, summation, square of the Fourier coefficients and multiply that pi. Okay. All right. The right-hand side, you need to calculate square of f on that period. Yeah. Yeah. Very easy. You can calculate 8/3 times pi cube. 1 pi you can cancel out. After simplification, you can get this summation. Summation of reciprocal of n squared, consecutive reciprocal of positive integer n squared equals pi squared over 2. Okay, nice result, right? Nice result. Okay, think about if I cover this right-hand side, pi squared over 2, I cover. If I ask you to calculate summation of the reciprocal of n squared for all the consecutive positive integers, how to calculate that? Very hard, right? Very, very hard. Yeah. In history of math, yeah, to calculate this one, it's very hard. In history of math. Yeah. But from this Parsifal's identity, so easy. Yeah. Yeah. Here you can see, with this example, you can see, with Parsifal's identity, we can prove many interesting summation results. Yeah. Many interesting summation results. Yeah. This is the first one. We have several more. Okay. Yeah. Several more. Yeah. For example, later you need to calculate to the fourth. Reciprocal of n to the fourth. Parsifal's identity. In your homework assignment, yeah, you will have one such question. Yeah. And the final, yeah, will also have one such question. Okay? Yeah. Yeah. All right. But because the Parsifal's identity, remember the square thing, right? Square of the Fourier coefficients. Square. Yeah. With that, you cannot calculate n cube. You cannot calculate n cube. Odd number. N cube, 1 over odd number, because it cannot come from square, right? Yeah. Yeah. How to come from square? Yeah. Yeah. When you do integral things, how can you get that from square? And actually, this summation, yeah, yeah. Matthew, yeah. So for the summation with even exponent number, this all even exponent numbers, the closed form is available. Closed form means pi something, pi certain square over some integer number, closed form. But the odd, this one, there is no closed form. This question related to a very famous math problem in the world. Very famous math problem. Have you heard of what is the biggest math problem in the world? Most important problem of math in the world. The top one. The absolute number one math problem in the world. Riemann hypothesis. Riemann hypothesis. That's the biggest one, okay? The biggest one, Riemann hypothesis. And this one is, some special case, in the Riemann hypothesis. Because Riemann hypothesis study the summation, so actually, n from 1 summation 1 over n to the s. That s is a constant. That s, not just constant, it's a complex number. Not necessarily a real number. It's a complex number, okay? Complex number. Study that expression, okay? The zero, because this expression on the what s, this summation takes the zero. For complex, it's possible, okay? It's not a real number, complex number, I, That Riemann hypothesis, describe the hypothesis, okay? So the distribution of the zero of the s, very interesting distribution. So, because the complex, you can write complex, represent complex on the plane, right? The plane. So Riemann hypothesis, the zero is located on this s equals 1/2. All the zeros distributed on this line. That's the Riemann hypothesis. The most important math problem in the world. So here, related to this summation. When s equal to 3, this summation, there is no closed form. There is no closed form. Okay? All right? So too hard. Nobody knows how to calculate. Okay? Nobody knows how to calculate closed form. But for even, so by possible identity, we can calculate all of them. Okay? Even terms. Even. All right, so that's something. B.3 from Fourier series to Fourier integral. Next, we need to move to the Fourier integral. And that one, we need to derive the Fourier integral from the Fourier series. So let me do some preparation. If I cannot derive today, so let me just do some preparation. Extend Fourier series to Fourier integrals. Why do that? Why do that? So here, because for the Fourier series, when we apply Fourier series for a function, we only consider periodic functions, right? Periodic function. Then it is very limited. Periodic function, it's a limitation of the functions. How about if a function is not periodic function? Okay? Fourier series cannot be used. So here we want to consider if the function is not a periodic function, we can extend this tool to non-periodic function. So we will use the Fourier integral as the extension of the Fourier series for non-periodic function. So it's important. For non-periodic function, so we have another tool, different tool. Okay, so here, two different tools you can use. For periodic functions, you use the Fourier series tool. Okay, this tool, Fourier series. For non-periodic functions, you cannot use Fourier series tool. You can use the tool of Fourier integral. Fourier integral, a different tool. Okay, all right. So let's look at the connection. How to do the extension? Yeah, powerful tool with limitation. Now, yeah, limitation for the non-periodic functions. Yeah. 2, domain is the whole x-axis. Yeah, because periodic domain is on one interval, right? One interval. Yeah. How about arbitrary function defined on the whole x-axis? Then you cannot apply the Fourier series. Okay. Arbitrary function defined on the whole x-axis. How can you? You cannot apply this Fourier series, the tool, right? Yeah. So that's the limitation. Yeah. Now we want to find a way to represent a function even with these properties, non-periodic, defined on the whole x-axis, we can still calculate. Yeah.
So in the last example, we had the sawtooth function.
Yeah.
You limited the domain to -5/5 for that reason.
Oh, it's not for that reason. That's sawtooth function because in engineering applications, it could be used in many places. Yeah,
Right.
yeah,
But we have
yeah.
to limit the domain. Like,
Oh, limit domain.
right here it says it doesn't work if the domain is the whole x-axis.
Right.
But we just did. And the domain of the sawtooth function is limit from.
Yeah. Well, but that's a periodic extension. Yeah, that's okay. All right. That's the key point. Yeah, because if you have a function without periodic extension, but it occupies the whole x-axis, then we cannot do. So what you can do, you work on the periodic function. Yeah, periodic function. Okay, but the essential part is still limited on one interval, right? All other parts just repeat it. Yeah, yeah, yeah. So that's the difference. Here we want to drop that limitation. Okay, yeah. Like e function. E function, you cannot use that way to describe, right? E function, covers the whole x-axis, without any period. Yeah. Then you need to find a different way to represent it. Yeah. All right. Yeah. Let's continue. Yeah. But when we start, we want to start with the periodic Fourier series. Yeah. But the idea is we want to make the connection. The Fourier series and Fourier integrals, because we have the experience. When we do integral on the whole x-axis, think about. Yeah. I don't know if you have this experience. Yeah. When you calculate integral on the whole x-axis, can you break the whole interval into pieces? Right? Yeah. Think about. Can you represent in this way? Yeah. So here I need some space. Yeah. All right. Can you do it? Yeah. Let's say capital K plus 1. Yeah. One interval, with length 1, f of x dx, but I take summation. Capital K from negative infinity to positive. Can we do that? Right? Yeah. Yeah. So we break it. Yeah. There, on each interval, can we? Right? Yeah. So this kind of connection. Yeah. We may have some technical difficulties, but connection is like that. Okay? But how do you connect summation to integral, right? Yeah. So this observation is this kind of observation is the connection. Yeah. All right. So let's take a look. All right. Now, capital F. Yeah. So here, because here we use this capital L as the parameter. Do we have freedom to choose capital L? We have freedom to choose capital L, right? make larger, make smaller, yeah. Yeah. But when we change that L, yeah, so there, our integral looks different. Yeah. So here we can, delay the, the choosing value of capital L. Yeah. All right. So for the L, yeah. So we do the Fourier expansion like this. Yeah. Okay. All right. Yeah. So here you can see summation from negative L to L. Summation. Okay. Yeah. All right. Yeah. So then you try to combine them. Okay. The summation, because when you do summation, can you combine the summation to that integral from negative infinity to infinity? Combine the summation. Okay. But because when you have summation, you can combine the summation from negative infinity to infinity. Okay. Then summation is gone. You just have the integral. Okay. You just have the integral. Okay. Yeah. All right. Yeah. So in that way, you replace. So here, you can treat it in this way. You want to get inspiration. Yeah. Here, we want to discover something new from the old result. Yeah. But we want to get inspiration from the old result. Yeah. But when we do calculation, yeah, sometimes there is a possibility there is some gap there. Yeah. So you don't worry about the gap, okay? Yeah. You just do it. Yeah. Euler did this kind of thing a lot. Yeah. In Euler, some of the calculations, there is some hole there. Yeah. So not very rigorous. Yeah. But just do it. Yeah. And see if there is some interesting result you can derive. Okay. Yeah. After you get interesting result, then you try to prove it. Okay. Try to improve it. Yeah. Try to fix this place, fix that place. Try to improve it. Yeah. Yeah. So a lot of things like that. Yeah. So when you try to get something interesting, new results. Yeah. So you do something. You may have some gaps here and there. Yeah. So don't worry, just do it. Yeah. Yeah. And after you get something interesting, so for example, this is something interesting, then you try to see if this is really true or not. Okay. All right. Yeah. So next time, yeah. So I may explain a little bit. Okay. So if we want to see how to combine the summation to get this integral. Yeah. So I may give you a little more explanation. Yeah. Yeah. But the result is correct. Okay. Yeah. So try to convince you. Yeah. We can do it this way. Yeah. All right. Yeah. So let's stop right here. Yeah.